with the next talk of the morning. Ken Baker, who will tell us about constructions of asymmetric L-space knots.
Well, it truly is a pleasure to be here, and I quite appreciate the opportunity, well, the invitation and the opportunity to share with y'all some of the work, 2 bits of work that I've done with 2 sets of collaborators. The first part will be work with Neil Hoffman and Joan Licata. The second part will be current work with John Luecke. And put these together because they kind of all fit together in a similar theme. But maybe we'll start off just kind of laying the context for all of this, and I'm very thankful to Yi for establishing several of the definitions. So that definitely makes our work easier to have seen some of this before. Slightly different notation. I'll be dealing with a knot K, say in a 3-manifold Y, and then it will have some sort of Dane surgery, say along the slope gamma, to give us a surgery dual knot K star and a surgery manifold Y star, which maybe I'll often write something like Y sub K of gamma. So I think Ni had these flipped, but I'm going to do it this way. In fact, he also mentioned I think the motivating conjecture here, and so I'll just put this as item 0. I can ask, well, what if I have a knot in S3 and I have a surgery to go to some knot in, well, where we have a lens space. Right. And this whole situation here, this is the Berge conjecture, or trying to understand the classification of the knots in S3 that have surgeries to lens space. And succinctly, this just says that K is a Berge knot. Well, I don't think Berge called it the Berge conjecture, called these things Berge knots. So maybe it's better to say it has a doubly primitive presentation. And don't worry too much about what that is. I'm not really going to fixate on any of that this talk, and we'll maybe come back and be able to say a couple of words there. But one thing to note about this is that having a doubly primitive presentation implies that K is tunnel number 1, meaning you can just drill one arc out of the exterior of K and end up with a genus 2 handle body. And one consequence of being tunnel number 1 is that K is strongly invertible. So I'll give an example in a little bit of what we mean by strongly invertible here and kind of how it plays well with Dane's surgery. So if you're wanting to think about this Berge conjecture, you might say, well, this is a hard question, and let's try to think of related things. So you might try generalizing in one way and say, well, S3 is a special kind of lens space, so we'll just deal with K in a lens space and say, well, what happens if it has a lens space surgery? And you can ask kind of these same questions. Does it need to be doubly primitive? Maybe just tunnel number 1, or maybe just even weaker, does it have to be strongly invertible? So that's one way you could try to generalize this question. Another way you could try to generalize this is to realize that, well, S3 is the double-branched cover of the unknot, and lens spaces are double-branched covers of 2 bridge knots, or links, which these things are all alternating links. So you could just say, well, what if I was going to have something that went from the double branch cover of the unknot to being the double branched cover of a alternating link. Right. And then you could ask those same questions. Well, maybe not doubly primitive, but you can still say, must it be tunnel number 1, or must it be strongly invertible? So you could ask those questions about it. This doesn't raise up. But in fact, maybe I'll put a 2' in here. And, well, this double branch cover is S3. So there's this other situation of just saying, well, having a knot in S3 and these double branch cover of alternating links, and maybe I need to throw in the word non-split. But these are special cases of L spaces that we've heard about. So you could say, well, if I have a knot in S3 that has an L space surgery, in other words, that K is an L space knot, does it have to be tunnel number 1, or does it have to be strongly invertible? In fact, it's already known that there are examples of cables of torus knots that are not tunnel number 1 and yet are L space knots, but those are all still strongly invertible. And in fact, so there's a conjecture, which, as far as I can tell, Watson's the first one that wrote it, but I think several people thought it. I don't know if Watson really wants to own this anymore. But L space knots are strongly invertible. All right. So, well, what I'd like to do today is then I'm going to tell you about these 2 items, and I guess this, as a consequence, this third item. And maybe to begin with a little bit more, I want to just kind of remind people, because it will be useful for what we're going to do. I'm going to remind people what it means to be strongly invertible, okay, and just and then how that plays nicely with Dane's surgery. So, well, I'm going to draw almost the exact same picture you started off drawing, and then we'll embellish it. So, what do? Well, we draw the trefoil, because we always draw the trefoil. Wouldn't be a talk if we didn't. And I'm drawing it all thickened up here, right? So this is the trefoil, and so we'll just use this as a model of our knot K and S3. And let's see, let's use this. So it has its meridional slope here, which bounds a disk in that solid torus. And well, I could think about taking a different curve in the boundary of this solid torus. So which one are we going to do? We're going to kind of do the one that goes along here, maybe goes under, goes over, and comes around, maybe under. I'm doing this one because I know what it is when it's one to kind of understand what's happening a little bit easier. So I'm going to call this curve maybe gamma, and we'll do the Dane surgery, the gamma Dane surgery, and this is where we get well, S3K of gamma. All right, so that's Dane surgery. I'm going to instead drill out this blue solid torus and fill it in with a red solid torus so that the red curve bounds the disk. All right, and that's going to give us some manifold. And you can ask, well, which one it is, and there are various tricks to figuring it out, but here's one trick towards figuring it out, and it starts with the fact that this knot is strongly invertible, by which I mean that there's this axis that I guess actually punctures through here, and it goes through, and then it goes between these 2 strands, right? So those are over, and the axis goes between them. And then the point is that we have this involution where we can just rotate around this axis. Okay. So just you do 180 degrees. That green axis is just an unknot, right? And so we can just kind of rotate everything. So because the trefoil is strongly invertible, and maybe let me go ahead and draw the kind of the core here, because that will maybe be a little helpful to see. You notice that the core of this thing intersects that green axis just twice there. And in fact, this mu, we get this, that inversion brings that to another curve over here that gets intersected once. Okay, so that's the image of mu. And what we can do is we can quotient by the involution. All right, so I'm just going to show you the result of all the isotopies and everything that goes with this. But it's kind of a fun exercise to try to see. You can double check that I do this picture correctly. So it's at least certifiable if I'm correct. correct. So I'm going to take this, and then this white torus that I had out there becomes a sphere. And what? Well, it becomes a sphere that contains two arcs, and you can see this arc and that arc are going to become these two arcs here. This blue disk that misses those two arcs will become this kind of equatorial disk here that separates those two. And the brown arc there, that's the core, just becomes this little arc that punctures that blue disk once and joins these two bands. And really this white sphere now is just a neighborhood of that brown arc. Right? So for some reason I like to do like either a kappa or kind of a curly lowercase k or something like that for down there instead of the k up there. And what happens with the red curve? Well, in this picture, the red curve descends to this curve here on the sphere. And it's got its image under the involution. You might want to move it around to make it so that it doesn't intersect the green axis, but you can do that. And well, what's the point? I want to do Dane's surgery, but now I want to think about taking this rational tangle here and changing it. So what we can do is what's called a rational tangle replacement. And well, that's going to just change this thing. And how does it change it? Well, I want to make sure that this red one is going to bound the disk now, because when I do this Dane's surgery, the red curve is going to bound the disk. And so when I have these green arcs coming in, I mean, it should just kind of be like this rational tangle that had the blue disk. It's going to just miss, we just need these arcs to miss that, that red disk. Right? And we can get the dual arc here. So we have this dual arc kappa star. And well, the point then is that if I go back up this way by taking the double branched cover, so I'll take the double branched cover of S3 branched over the green curve, that should give me the surgered manifold up there. And in fact, we can go the other way here. You might recognize that this thing is just the unknot, right? So this is the double branched cover. And whatever is coming back down to here, this is the quotient of some involution, the inverse of that. And if we look, this thing here, well, you can maybe already see, but let me go ahead and take this arc and flip it around here. And I'll do one other trick of taking that little thing and swapping it over. So you can actually see it as, I guess I want to do it like this. Doing it like this. So I can actually see this as the connect sum of the Hopf-Link and the trefoil, which then tells me that this manifold here is L21 connect sum L31. Right, so just by looking down there. And also one thing you can notice is that after moving that over and then doing that little flip, that's an alternating. So this is also a double branch cover of an alternating. Right. So, you know, looking at, say, number 2 here, the conjecture here, or one statement is that if you had such a surgery, it always occurs in such a manner. Okay. All right, that's kind of the general idea, and then you don't have to be in S3 to have something like this occur. You could be in a lens space or other manifolds that have such a strong, like this involution with a fixed locus of a sort. Okay. So this is kind of the, in some sense, the expected context. This whole thing, this trick of viewing Dane's surgery by passing down there is often referred to as the Montesinos trick. All right. So we're actually going to use that trick in various ways, and you know, and try to be a little bit sneaky with it. Right. So this brings me to talking about number 1, and this is where it's joint work with Hoffman and Licata. And this starts with the theorem of Dunfield-Hoffman and Licata. Well, what do they say? Well, what they say is that there exist, I guess let me phrase it this way: there exists hyperbolic, asymmetric knots in length spaces with length space surgeries. Okay. So, in particular, well, let me actually just kind of define what we mean by this. So, given a knot K and Y, such that, well, let's just say, is a hyperbolic asymmetric, if the complement of the knot is a hyperbolic manifold, let's call it maybe X. If the complement is a hyperbolic manifold with trivial isometry group. There's different variations of what you might want to do for calling something asymmetric, but we'll just go ahead and use this for our purposes. And this is basically the definition they used here. One thing that you can immediately notice from this is that, and this implies one, so one, it needn't be strongly invertible. Otherwise, there would be an element of order 2 in the asymmetry group. So, yeah, so, I mean, you could say, well, then we're done. But, you know, I mean, this is a terribly provocative statement, you know, because, and what made it so, like, intriguing is that they found it just through a computer search. So there was this very clever search of the SnapPy census of hyperbolic one-cusped manifolds with, I guess it's up to 10 tetrahedra in their composition, and did some various checks, but could ask SnapPy, well, your hyperbolics, so tell me your isometry group. Let's look at the asymmetric ones, and then let's just do something about, let's look at the fillings along the two shortest geodesics, or sorry, two shortest slopes in the cusp, and you know, if I calculate that you have a fundamental group with a single generator, well, then that means you've got a cyclic group. And okay, so this is something that, you know, with a little nudging, you can get a computer to spit out a list. And I guess people like Nathan and Neil and doing are pretty good at nudging computers. So anyway, they got this nice list of, what was it, 22 manifolds. And you're like, wow, that's great. Where do these guys come from? Right, so what you really want to know, or at least what I was left knowing, and there's some nice coincidences of me arriving in Australia and being on the airplane when they were doing this, that I got to front row seats and like examining these examples. So what came out of this through talks with Joan and Neil during that trip is, well, a construction that I want to share with you. So let me just rephrase it like this. This is a construction. Right. And so let me just kind of cut to the chase rather than kind of give the long story of the buildup of how you do it. So there's one key idea that comes in from, I guess it was from a paper of Gordon in the like 87 or something, or 89. But there's this idea where, and I'm going to give just in the situation that we're going to use it here, but there's a generalization. So if you have a pair of curves, let me call this like k plus, k minus, embedded in the boundary of a H, where H is a genus, well, a genus G handle body, but let me just say genus 3 handle body. Well, let's just say genus G handle body. is what we could call jointly primitive. Jointly primitive if there exists a corresponding pair of disks, ordinal disks of the handle body, d plus and d minus, such that ki intersect dj is just the either 1 or 0, and where we're going to let I and j be, plus or minus. Right, so what's the picture of this? The picture here is, so then up to homeomorphism, and let me just draw it with a genus 3 handle body. So this is H, and what do we do? So I could imagine here's K plus, here's K minus, and then we're getting these disks D plus and a disk D minus. All right? And so that's up to homeomorphism. This is what it means for those curves to be jointly primitive. And the nice thing about this is that when you look at what happens when you attach two handles along K plus and K minus, is that you end up getting, this whole stays where it is, but these other two kind of plug up. So you're just going to get these two kind of dual arcs, so like K plus star and K minus star. And then those disks D plus, that kind of becomes a bridge disk for that arc, and D minus becomes a bridge disk for this arc. Okay, and so we end up with a pair of bridge arcs in a solid torus. Right? So that's kind of the dual to having something jointly primitive. All right. So, okay, so then, well, what do we do here? So what I want to do is think about, so I'm going to define a new kind of property of knots in three manifolds. So we're going to take a knot in a three manifold Y, a closed orientable, whatever, three manifold Y, and I'll throw in the next word here, something jointly primitive presentation of K and Y. Well, what do we need from this? Well, this consists of a link C1 union C2 and Y together with a twice punctured rational Seifert surface, sigma. So sigma is some twice punctured torus that's properly embedded in Y minus the exterior of C1 and C2, so that one boundary component of sigma is on each of these torus boundary components. Okay, and so that what? Well, so that, and let me leave one thing off there for a second. Well, so that, well, you have that, where did I want to phrase that? Well, yeah, so that, I guess we want K embeds in sigma as a non-separating curve. Yeah, and I guess let me go ahead and call this thing M. And what? So if I look at M, cut along sigma is a genus. There's three handle body in which the impressions of K, the images of K, the images K plus K minus of K are jointly primitive. Yeah, jointly primitive in H. Okay. Yeah. Well, there's a genus 3 handle body, and I guess this could be the next point. Okay, well, before filling in that other thing, I mean, let's just see what that does for us. So, well, what's the overall picture? Here we have, maybe here's C1, C2. I'm thinking of this somewhat like a cross-section, but not exactly. And then I have this twice-punctured torus sigma. And what color we were using? Oh, let's just use purple here, I guess. And then here's going to be my knot K. And then all this stuff out here, all this stuff out here is supposed to be some handle body, some genus 3 handle body out there. And then the idea is that when you, if you were to do, if I do 0 framed, well, I say 0, this is like sigma framed surgery on K. Well, what happens? Well, on one hand, from the jointly primitive property, we have H, and then we have these 2 images, I guess. We have the K plus and the K minus. So we think about adding those 2 handles here. We get this. We saw that's a solid torus. But then we're left with being joined to that, while we still have the neighborhood of C1 and the neighborhood of C2. Well, this thing, let's call it sigma star. And just to be clear, so this, if this is sigma, then our knot K is this non-separating curve. Right? And so when we're doing surgery on K sitting in there, and we're doing the sigma framed surgery, what that does is actually kind of the 2-dimensional surgery on that surface as well. We're going to kind of cap, chop along K and cap those off with the meridional discs of filling. So what ends up, what is sigma star? Well, let's just do it. You can just draw these pictures. And just, we've cut open here along K, and then we cap off. And this thing, if we kind of just suck that all in, you see that we actually just get an annulus. So this is an annulus. So what we have here is we've got a solid torus being glued to 2 solid tori joined by an annulus. Right, so this whole thing ends up being a small Seifert fibered space. So a Seifert fibered space over the sphere with at most 3 exceptional fibers. And we can see the exceptional fibers, this, and then whatever's the core of this handle body. Potentially it's like a degenerate Seifert fibered space, or potentially there's maybe even fewer. Okay, but in general, we don't have control over that. If I want to get a lens space, well, that's a special kind of small Seifert fibered space. It's one in which one of these fibers is not an exceptional fiber. It's actually a regular fiber. And well, how do we make sure it's a regular fiber? Well, we can just ask that. Sigma intersect the boundary of neighborhood of C1 is the longitude of C1. And so maybe we can just call this longitudinally jointly primitive and abbreviate it LJP. So a longitudinally jointly primitive presentation then makes us end up have that when it's a longitudinal jointly primitive presentation implies we get a lens space. Okay. So we can say a little bit more here. So what have we done so far? We've just started off with this manifold Y, and we've gotten this dual manifold Y star. So we have that when we have a longitudinal jointly primitive presentation of a knot in some 3 manifold Y, we arrange that it has a surgery to a lens space. And so what we want to do is say, well, can you find longitudinal jointly primitive presentations of knots in lens spaces? Right? And so I want to at least spend the next maybe 5 minutes just suggesting to you that these are abundant. In fact, maybe let me state a little bit more of a theorem here. A little bit more comes from this construction. If you actually use this, fact, let's just draw it over here. When you have this longitudinal jointly primitive presentation, thinking of that as a well, I guess we did that as longitude. I mean, so we think of C2, and so this boundary of sigma, if this is actually the meridional disk of C2, then we can think of that annulus as maybe wrapping around here several times, and then we just see C1 kind of coming around like this. And so, you know, here we can see this would be maybe our Heegard torus, where we have like H star out there. And from these two, you know, these bridge disks here outside, and then what's happening with this, I guess you get these two dual spots. So the knot K star is going to be intersecting this annulus twice, and then we have those two bridge disks out there. So basically what we're seeing is we have two things like that, and then, I don't know, one of our bridge disks could connect it up like that, and another bridge disk here. This also tells us that we have a two-bridge presentation of our dual knot in the lens space. And if you're very careful, you can actually show that any time you have a two-bridge presentation of a knot in a lens space, two-bridge with respect to the genus 1 Heegard torus, anytime you have a two-bridge knot of something in the lens space, then you can do surgery to come back to a longitudinal jointly primitive presentation. So this is very general in terms of, you know, as soon as you have a two-bridge presentation, you have a longitudinal jointly primitive presentation dual to it. But you still need to find this thing in lens spaces. So let's just write this out. So what I was just talking about was this proposition. If K and Y has a longitudinal jointly primitive presentation, then Y star being this YK, the sigma framed surgery is the lens space, and the dual knot K star, and Y star is a 1-2 knot. I mean, it could be a 1-1 knot or a 1-0 knot, but it's at least two bridge. Yeah. So, and then the theorem here, and this is maybe just a general statement that there exist many asymmetric hyperbolic LJP knots in lens spaces. So in particular, I mean, I'm just claiming that we can actually do this a whole lot, and I'll give you an example of a large family of these guys. And secondly, each of the DHL knots arise in this manner. So in all of the knots that Dunfield-Hoffman-Licata found, we actually have been able to find longitudinal jointly primitive presentations for them. And well, I guess we don't need that anymore. So let me just give a quick example of these, of one family of these. So kind of the initial families we found, we started with this exterior M being a cable space. Those are some nice things, and in fact, you can find the cable spaces that have twice punctured tori in them. There's only up to homeomorphism 2 of them, and let me just show you one of them. But they both give us large amount of families. So what I'm drawing here is the 2-4 torus knot, or torus link. Okay, and so let me call this like C1 prime and C2 prime, because we're going to want to do surgery on those as well to get our jointly primitive presentation. And just as an example of one of our knots, I guess we were using purple. So just to give a concrete example of one, I have these curves here, and then I'm going to maybe have 2 coming around this way. So this kind of, you know, they've got that twist there, and then these are going to come over like that. Right. But really, we could start twisting a whole bunch of times around here. Right. So we'd get an entire family, Kn. And they're living on this, you can see the visual twice punctured torus here. And you might note that's a fiber. And so what are the jointly, just to see that it's jointly primitive, when you thicken this up, well, one disk you can see is kind of just coming from right here. When you've thickened it up, that will be one disk in the kind of complementary handle body. The other disk is a little bit trickier to see, but let me give you a recipe for starting it. So if this is, say, D plus, let me just draw this and call this a pre-D minus. What I want to then do is, I have all these extra, under here, this is touching, this green disk is touching from one side, whereas that's touching from another. What we want to do is we want to start, we want to just start spinning. I want to get rid of these intersections here. And so what I'm going to do is I'm just going to tube, we can just start kind of tubing this and over there and tube it along many times. And that will be enough to make that the correct D minus. And so all you have to end up doing is doing some surgery. So, to get to be longitudinal jointly primitive, I need this -2 minus 1 over b for an integer b, and then for this thing here, so that we can get a lens space rather than a small separate fibered space. Well, I also see, well, you can work it out. This is a +2 minus 1 over a. So all of these tend to be, these surgeries will give us a longitudinal jointly primitive presentation in a lens space. And let's just kind of observe quickly why, you might say, well, that looks strongly invertible to me. Can't you just flip it along this axis, right? And so the key thing, though, is that when you flip it along these axes, while K is strongly invertible with respect to that involution, what you're doing is you're exchanging C1 and C2, okay? And so to destroy that symmetry, you just need to make sure that these surgery slopes are different. Yes?
So when you say tubing, you actually mean banding, right?
Banding, yeah, sure. Tube with a half of a tube. Yeah. Do what you need to do is what I'm saying.
Okay.
Yeah. Anyway, so this works, and in fact, you can express this as a this family of twists as altogether you get it like a 5-component link, and you can throw these things into SnapPy and confirm that you are getting asymmetric manifolds that actually have the required surgeries. And so anyway, we've done that with all of. We found many of these kinds of things. I'm happy to tell you about more later, but maybe we'll get on to number 2. All right. So, and just a little brief note. In doing so, of these asymmetric hyperbolic examples, there were no interesting surgeries to S3, and there were no interesting surgeries to S1 cross S2. Any ones that we found of those were either they were all strongly invertible and known examples. Yes?
Which lens spaces are we seeing in this?
Yeah. Well, that's a good exercise, right? So first, just do the surgery, right? Okay, and then do that surgery, and then you get lens space. I can show you afterwards. I don't know off the top of my head, but I can give a more complete picture and more. If you don't believe that this is giving you a lens space, I'll reinforce it later. All right, so I have like 25 minutes to tell you more-ish, or is it just 20 minutes now? Well, we have a break afterwards. I have like 50 minutes. Okay, so, okay, so this was already known. Dunfield-Hoffman-Licata said these can't be strongly invertible, but now we have a sense of understanding it better, and maybe ways of kind of seeing more. But you could, okay, there's more questions you can ask, but I should stop babbling about it. So now I want to move to this second work here. Looking at these alternating links, and well, this starts with a trick, and so that, in fact, I guess it started with my younger mathematical brother, Sean Bowman, who employed this one technique to do some interesting, show that a surgery on a knot in a handle body that gave you back a handle body. Well, that knot didn't have to be one bridge in the handle body, in contrast to what happens in solid tori. In fact, Luecke, after the next talk, is going to tell you some of our further work on that. And this next construction I'm showing is what kind of grew out of Sean's work and then our joint work together and trying to understand a particular operation we're doing better. So I'm going to give you a completely digested version of this, okay? So, well, what do we have? So I want to think of taking a pair of pants. Okay, so this is some pair of pants P, and maybe I'll go ahead and pass to thinking of these curves as blue to hopefully get some color sense to all of this. And I really want to think about a pair of pants cross-I. So what we're doing is just doing the projection in this pair of pants. Okay, but I've got this genus 2 handle body, which I want to view as pair of pants cross-interval. And inside this pair of pants, we have a punctured torus. So let's see, and then I'll do something like that. All right, so here's a once punctured torus T sitting inside this pair of pants. And let me draw some basis curves on there. Yeah. So I'm going to let this here, and I'll let that be lambda. And let's take this other one over here to be mu. Okay. And what I want to say is, what we're going to be doing is we're going to take this genus 2 handle body, this pair of pants cross interval, and we're going to be embedding it in 3 manifolds. But this is somehow this is a template or kind of a carrier for knots that have interesting surgery properties, or at least give some structure to some interesting surgeries. And the family of knots we're going to do are going to be the slopes on this torus. And maybe it's not so apparent from this picture, but I kind of like to think of these slopes, some curve that's wrapping around this a whole bunch of time, it's kind of lashing these 2 holes together. Or if I think of it thickened, I've got these 2 posts, and you're kind of just winding this knot around. So it's kind of a, anyway, so I've taken to calling it a lashing of P. And there's some choices in how you're lashing, but let's not worry about that. Is a knot K, or if I want to be more specific, I'll call it KPQ, which, with respect to this basis is P mu plus Q lambda in homology. But this is sitting inside that torus, which is inside this P cross I. This is our torus T. And maybe to just note a few things, this green curve here is actually isotopic to this blue boundary. I'm going to call that one C lambda. Same thing here. This is C mu. And this boundary out here, it's C nu, where nu is, I guess you can take it as lambda minus mu. You might be interested in knowing about lambda plus mu. And maybe the rest of y'all too, but so what happens here? So the first lemma, is to say, well, what happens here? So if I just think about P cross I, this genus 2 handle body, and I take my PQ lashing K in there, and I do, well, it's not 0, this is like T framed. T framed, but it's planar there, so we can just do like blackboard framed. That's the framing we're using, which is convenient. Okay, so what is this? Well, I can just take P cross I, and I can I can just view it as surgery on this 3-component link. So I'm going to do new mu lambda, or new lambda mu. And the result of this is I get a +1, and I guess want to do a minus Q over P plus Q, and minus P over P plus Q. All right. So the claim is that we have this surgery equivalence. And so if you were thinking about the curve lambda plus mu, you have this curve with 1 crossing in the projection to the pair of pants. And you get like a 1, and then a -1 over 2, and a -1 over 2. And so we're actually seeing this kind of fiber-preserving kind of surgery in that special case. But otherwise, it's not necessarily a fiber-preserving surgery. And so since I went ahead and somebody convinced me to go ahead and draw some more pictures, so there we go. So if you want to see this kind of stuff, This is just kind of the highlights of the surgery calculus that gets you there, going down the left and then down the right. But so we can express curves in this once punctured torus by just these Dane twists, these pairs, and I'm running out of time, so you can stare at that while I talk about something else. Yeah, okay, well, let's go down to here. All right. There we are. Okay, so this construction and right. So what do I want to do? So my goal here is to do something about well, knots in S3 that have surgeries to double branch covers of things, but maybe that are not strongly invertible. Okay. So how am I going to do that? Well, the way we're going to start is I'm going to start off with this genus 2 handle body. And well, if you have curves, and this might not be, I'm not really thinking of these blue curves now as bounding disks, but I can kind of think, there's a pants decomposition of a genus 2 handle body into 2 pair of pants where they share their boundary components. So I might think of this as P and maybe some other pair of pants Q. And, but the thing is, like, using the hyperelliptic involution, I mean, you have this axis that goes through here. So you have this quotient here. And any pants decomposition, the 3 curves that bound the 2 pair of pants, those will be strongly invertible under this hyperelliptic involution. Okay. But the thing is, you're exchanging P and Q, right? So maybe you wouldn't expect for this junk over here in P, maybe they're not going to, because they're getting sent off themselves somewhere else, they might not necessarily be able to be isotoped to be invertible by at least this axis or this action. So there's a it seems like maybe you do put some knots over here in P, they might not be strongly invertible, right? And maybe you have to put them in there in the right way, but and this is kind of like what we saw in the other one where we had the C1 and C2 and it was swapping them. So you're doing something to destroy a symmetry, okay? Or at least destroy the obvious symmetry. So this is where I think these things are similar. And well, what's the point? Well, this is let's just do it schematically first. I have this quotient. C mu, nu mu, lambda mu are strongly invertible, so I can go ahead and take the quotient. And I'll just leave this very schematic. Here's my Heegard surface. If I'm in S3 or something, I can have some flat presentation, yeah? Some braid up here, and I get some nice 3 braid. Let's put some of that there. And the thing is that these 3 curves end up giving me 3 arcs on the Heegard, on the bridge sphere, where I can pay attention to them. And so maybe this is C nu, C lambda, C mu. This is curly little c nu, curly little c lambda, and curly little c mu. And well, I mean, because by this lemma, if I want to do surgery on a lashing in P, I can just instead do surgery on this triple of curves. But those triple curves are strongly invertible. So if I want to do S3 K, 0 for, this is for a lashing K, or P, Q, lashing of P. So that 0 is that framed surgery. Well, I know then by the lemma that this is C nu C lambda C mu 1 minus P Q over P plus Q minus P over P plus Q. Right. And so by the Montesinos trick, just applied to all 3 of these, we can do the rational tangle replacements and get something that has the double branch cover up there. So let me just quickly show what these pieces are. I'm going to give it a little bit more space and to describe these resulting tangles here for whatever you put down there. So what do we have? Well, the plus 1 ends up being this kind of twist. And then these, it's related to the braid, the PQ. And maybe I can just draw it like this. So I'm going to put some 3 braid in here. I guess if I call it beta bar, I mean, well, I've got some 3 braid and then that I'm calling beta, and then I said beta bar because I'm flipping it over some way, and then here I get maybe minus beta where I've flipped all the signs of everything. I flipped it in a different way, and I could put it down like that. Anyway, these are rational tangles, and I'm claiming that you can find a beta corresponding to the PQ where these things actually end up corresponding to these here. So, you know, so there's a way of kind of producing the result, and then I know. The point is I can construct the you know, the resulting length that we're going to take a double branch cover of. Right. So. Yeah, okay, good. 10 minutes, we can do this. All right, so what I need to do for you now is to actually draw you I guess I tend to call these things J and J star. So I need to draw for you a 3-bridge presentation of the unknot, okay, in which I can do this kind of substitution and then show that J star is a alternating knot. Okay, and that will at least give me a knot that has surgery from the S3 to the double branch cover of the alternating. And then we have to maybe say some words about or argue that, in fact, you know, something about a symmetry. Okay, so there's 2 ways we can argue about symmetry. Well, there's lots of ways I can argue, but I'm arguing about symmetry. Okay, so, well, let's try this. So, let me go ahead and, I'm going to have 2 parameters to this presentation. So, yeah, that'll be fine. So I'm going to call this alpha, and what I want, 1, 2. So what I'm doing is I'm putting in a 3 braid that has this alternating presentation already. So I'm just going to set it up to have alternating as we need. And then let's just go ahead and continue this. So I'm going to have one more crossing down here, continuing that. That's going to go over, have this under, have that come around, squeeze that up a little bit. I'm going to put a little twist region in here, a whole bunch of twist boxes. That's something that's variable. That's going to come under. It's a presentation of a diagram of the unknot. So I'm going to make it an almost alternating unknot diagram. So this crossing here is going to be our de-alternation crossing. So what do we need? And then we'll have this other compensating twist box. Let's clean that up. Right. And then what do we need? We'll have kind of the companion to alpha here. This is maybe what I'm calling alpha inverse bar. So what do I mean by that? I'm going to have like alpha inverse, but then I flipped it over. So here I've just been drawing 3 twists in each just because it's easier to be a little suggestive that way. What do we need? Sorry, I had that. That's in the wrong spot. This one's going to come down under here. All right, there we go. We have a little cap here. That's going to be like this. And what's here? I'm going to put like minus M twists there and M twists there. So that would kind of, you know, that's what we need to kind of continue the alternating sense. All right. And so as it's surely clear, this is an unknot. Right. But actually, maybe I put a picture on there. But what do you need to do? You take this thing and you kind of flip it under here, right? And so this thing is going to kind of come over like that. Okay. You can already see these 2 guys are going to cancel. But once you pull that under, and then this little thing will be, this thing that goes under will be able to be more straight, and then you'll start to see it will all collapse. Okay. All right. So that's a way of saying that it's a unknot. And so let's see if I'm going to what do we have here? Hey, there we go. All right, so this is the kind of the more not friendly picture on there, and then this is the one that I think I just drew, and saying a little bit about that. So, well, I mean, so what's the point then? I can put this here, here, and here. Maybe I'll bring that down a little bit. And that's the C nu, C mu, and C lambda. And I guess in interest of time, maybe I'll just mess with this picture. So I want to insert those three tangles that I saw there. So what happens? This one's easy enough. I put in the +1 tangle. This one here, what happens? Well, I should have left myself a lot more space. Let's see. So we'll try something like that. So I pulled that down a little bit more. And what do we have? So I'm just going to put that in. And you can notice that top crossing here is exactly what I need to remove that de-alternation. And then we have this beta spot that, where do you put it? I guess I put it like that under here, and we had this. And then this guy gets erased and moved around. We also get the crossing here. And that's under and here, something like this. And well, the thing I'm not showing you at the moment is that you can choose the PQ, and in fact, if you just choose both P and Q positive, the tangles you put in here will continue the alternation. Oh, and I guess these cancel, so we can straighten that out, and these two cancel, so I can straighten that out. And then we get, you know, for alternating 3 braids alpha, and they're kind of partners, and you say positive them, so that's negative and that's positive, we get an alternating link. Okay, and one that's kind of whose double branch cover then is obtained by surgery on our lashing. And so let's go ahead and write out the theorem here. Do I have that as a picture? Hey, there we go. In fact, I even showed you some of these things. So that beta bar on the left starts off with a negative, positive, negative, and then the other kind of flips everything. Okay, so what's the theorem here? So using these things, with m greater than or equal to 2, and if we take alpha to be sigma 1 to the minus an, sigma 2 to the a n minus 1, I'm down to like sigma 3 to the minus a, sorry, sigma 1 to the minus a3, sigma 2 to the a2, sigma 1 to the minus a1. So if we take this with n at least 3 and ai are all positive. So if we do all that, then, and I could be more accurate here, but that would just take a little longer to describe. Then for, and I'll put this in quotes, sufficiently large P over Q, and really all I need to do is take a pair of curves that intersect once on that torus, and then twist one a whole bunch of times along the other, okay, and so that we end up with a positive slope, and that would be that would be sufficiently large. Then the lashing KPQ is a hyperbolic asymmetric knot with surgery to well, it's going to be the double branch cover of some alternating, and we can say expressly which alternating it is. So if well, I changed it already, but if I called the initial one with these parameters alpha and m, which are the parameters we have here, this is going to be the double branched cover. Well, we can just write here of like j alpha m, and then we'll have those nu, mu, lambda, mu, and we just put those tangles in. So, and well, we can leave that there. What do we have? All right. Well, maybe just a few. Sorry. Let me just take like a couple more minutes. Just a few more comments. But that's basically the construction. Oh wait. Oh, there's something. So anyway, as a corollary, Watson's conjecture is false. And a further thing we can show, these knots of our examples have tunnel number equal to 2. But I expect that to be able to we bump these up. And then as a further remark, can adapt to replace double branch cover unknot equals S3 with double branch cover 2 bridge equals lens space, including the double branch cover of the unlink equals S1 cross S2. So this proof easily adapts to give us, I guess maybe a 3 here, K in S1 cross S2 to, well, K star in double branch cover. So we can actually have these kind of null surgeries to, or knots and double branch covers of alternating that have null surgeries to S1 cross S2. So these what's called generalized unknots, L space unknots, for, yeah, whatever those things are called. They can be hyperbolic and asymmetric as well. So last comments. I actually, this sufficiently large can be rather small. But our techniques of proving this, we actually proved it without SnapPy. And this sufficiently large was part of kind of milking Thurston's hyperbolic Dane surgery theorem to say, well, we can do a lot of spinning and twisting to get something that's hyperbolic and, say something about what's happening a little bit with symmetry. But we actually end up showing that with things in this parameter, any homeomorphism will have to be isotopic to the identity, any homeomorphism of the exterior. So we actually didn't use SnapPy to prove this or anything. This was actually just straight up, 3-manifold topology, not without computers, I guess. But, of course, we want to use computers to see what we can get out of this. And in fact, sufficiently large, I could do like just 1 over 1. In fact, so we could use like Nee's example of the one crossing knot in the projection to do this with. And in fact, I actually only needed, I think it worked to have an example where it was just this, where A1 and A2 were 1. And I think M was just 1. Okay, so SnapPy, in wrestling with it, I'm not for a while, but was able to show me that, in fact, I had to get a surgery description, but we could find actually prove that we had a hyperbolic knot with asymmetric exterior and surgery to something that had a involution. And then I could go back and also say, well, I know what should be the quotient. I could draw then this quotient link and tell SnapPy to take the double branch cover, and with a little help from Regina, was able to actually find that had a hyperbolic structure. And then we could actually show that those hyperbolic structures were isometric. And so SnapPy actually gave a verification in a small case. And then further milking things, pushing things around, playing with surgery descriptions, I was actually able to kind of draw that knot on the Heegard torus, on the genus 2 Heegard surface. Well, with a projection on the genus 2 Heegard surface that I could then eventually make into a positive braid. And being in a positive braid, I could also enter that back into SnapPy and say, Now, was my surgery description and my positive braid description, are those the same? And it said, yeah, it is. And so in fact, so this is the smallest example, just through computer experiments I was able to find, of a asymmetric hyperbolic L-space knot in S3. If you take the closure of this, what is that? It's a 12-strand braid with length, so I guess 249, so that gives us a genus 119. And the 272 surgery produces the double branch cover of that 11 crossing alternating link. So that's like L12A955. The volume is about 10.2, and SnapPy tells me it has 13 tetrahedra in its exterior. So thank you.
The knots in S1 times S2, is it easy? I mean, what's the minimal number for each strand?
So the minimal I've found, I mean, so of course we can easily calculate what the minimal number of, what the braid index should be, because, you know, once you do this, I mean, the double branch cover of the alternating link, you can calculate the first homology from, and you know it's the square of the braid index. The order of that homology is the square of the braid index. So the smallest one I found was braid index 16. Yeah. I haven't yet obtained a presentation of the knot as a spherical braid yet. Just takes more time. But I mean, in principle, it's doable, and in principle, there's time. But if somebody else wants to do it, I'm happy to Sherpa.
If you take a knot in S3 and that has no symmetries and get a double branch cover of alternating, are the examples all integer surgeries?
Duncan would be the best one to ask about non-integral surgeries. So I'm not quite positive on what the status is on the answer to that question.
The examples you're finding?
These examples are all integral surgeries. Yeah. I should have been more clear about that. But we're doing the kind of the blackboard framing surgery from the projection into the pair of pants. So these are all definitely integral surgeries. I don't see where we're Duncan. Well, anyway, I mean, oh, there you are. I mean, so what's the story with non-integral surgeries on knots in S3 to getting double branch covers?
So if you have a knot with a non-integral surgery, which is a double branch cover of an alternating link, then there is a strongly invertible guy with the same surgery.
Okay, so then there's going to be some other guy that might have the same surgery.
So potentially this could give you something asymmetric, but
Yeah.
it would have a symmetric cousin as well.
So, yeah, I mean, I guess so then there's potential to find do some other thing kind of related with like a half integral surgery perhaps, but you'll get something that could also be obtained by surgery on a strongly invertible knot. And of course I should say, still didn't find any that gave us two bridge links. Okay. And of course, if you do use PQ equals 1, in fact, for the double branch cover here, I mean, you can see that's a 3-bridge presentation, so you get these genus 2 manifolds.